Now we shall switch over to the third chapter of this third unit. The chapter we are going to study is known as surface chemistry. We shall complete our study of surface chemistry by dividing this into following two chapters. Number 1, adsorption. Number 2, colloidal solutions. Let us begin with the chapter of adsorption. It is defined as the accumulation of a species at the surface rather than in the bulk of a solid or liquid. For example, adsorption of water vapors by silica gel. Terms involved in the study of adsorption. Number 1, adsorbent. The substance which provides the surface for adsorption is called adsorbent. For example, charcoal, silica gel, clay, colloids, metal oxides, etc. Number 2, adsorbate. The substance which is adsorbed is called adsorbate. Third, desorption. It is reverse of adsorption. Number 4, absorption. Absorption of a substance A by a substance B means that A is uniformly distributed all over B. On the other hand, adsorption means that A is present on the surface of B and the concentration of A in the bulk of B away from the surface is negligible. Example of absorption is water vapors are absorbed by anhydrous calcium chloride. Number 5, term is sorption. In some cases, adsorption and absorption both take place simultaneously and are indistinguishable. Such a phenomena is called sorption. Finally, occlusion. This term is applied for the adsorption of gases on the surface of a metal. Then we come to cause of adsorption. In the bulk of a liquid or solid, constituent particles, for example molecules, experience attraction on all sides, whereas molecules on the surface have neighboring molecules on the sides and below. Due to this, molecules at the surface experience a net attraction downward. These have higher energy than those in the bulk. The result is that the surface of a solid or liquid adsorbent is in a state of tension on account of unbalanced or residual forces. This can be understood from the following figure. Hence, when a gas or solution is brought in contact with such a surface of solid or liquid, the molecules at the surface of adsorbent tend to attract and retain the molecules of gas or solution, that is, adsorbate, with them. Thus, we can say that these residual forces at the surface of adsorbent are responsible for adsorption. For example, when finely divided active carbon that is activated charcoal, is stirred into a solution of a dye, the intensity of the color of the solution of dye is decreased. Similarly, when some gas is brought in contact with finely divided charcoal at low pressure, the pressure of the gas is further reduced. In both the above cases, molecules of dye or that of gas are adsorbed on the surface of the charcoal. Well, let us now learn properties of adsorption. Number 1, as we have already noted in the definition, the concentration of adsorbate is more on the surface of adsorbent and almost nil in the bulk. Hence, adsorption is a surface phenomena. Second, more is the surface area of the adsorbent, more is the adsorption on its surface. Because more surface area means more residual forces and hence more adsorption. That's why adsorbent are employed in the finely divided state. For example, if we have adsorbent solid cube of 1 centimeter H length, then it will simply provide a surface area of 6 centimeter square. But if it be broken down into smaller cubelets such that now the H length of each cubelet is 10 to the power minus 3 centimeter, then the total surface area provided by these will be 6 into 10 to the power 3 centimeter square. Number 3, besides dividing in a fine state, some adsorbents are given special treatments also. For example, when charcoal is heated at a higher temperature, that is from 300 degrees Celsius to 1000 degrees Celsius, in vacuum or in presence of an inert gas, it becomes activated charcoal. In this treatment, the already adsorbed gases such as hydrocarbons and other impurities on the charcoal surface are removed. The fourth point or the property is adsorption is a spontaneous process. That is, delta G for adsorption is negative. Fifth, adsorption is exothermic process. That is, delta H is negative. This can be understood by the following logic. Since molecules at the surface are in more ordered state than in the solution, and moreover, the translational freedom of adsorbate is greatly reduced, hence we can say that entropy change delta S for adsorption is also negative. Now from Gibbs equation, delta G equal to delta H minus T delta S at constant temperature. When delta G and delta S both are negative, hence delta H is bound to be negative. Sixth, entropy of adsorption delta H is defined as the enthalpy change for adsorption of 1 mole of an adsorbate on the adsorbent surface. For physical adsorption, this is about minus 20 kilojoule per mole, while for chemisorption, its value is from minus 80 to minus 240 kilojoule per mole. Finally, the seventh property, adsorption is further classified as A. Physical adsorption or physisorption, B. Chemical adsorption or chemisorption. A comparison of their properties is given in the following table.